podcast. This is Mr. White.
And Mr. Johnson.
And today we're going to talk about lenses. And that is a direct tie into refraction. So, Mr. Johnson, what was refraction?
Well, refraction was the bending of light as it transfers from one medium to another.
So, bending of light through materials change. Those were transparent materials.
Mm-hmm. The Pyrex pieces.
Right. Does it have to be light, or can any wave refract?
I think any wave can refract.
Yeah. So we're just investigating this wave phenomenon because
Mm-hmm.
light's the easiest way to do that.
Right.
Right, okay. A lens uses refraction, except it's very specific. When we think of lenses, I think about the glasses that I wear, maybe the contacts that some of our students are wearing.
Right.
And so this, of course, can be used for magnification or crispness of the image. And so this is the science over here. We don't talk about it a lot in here, but I remember teaching other science courses. This is the science. This is the technology. So this is an application of the science of refraction.
In this day and age, you just don't think of a pair of glasses as being technology.
Yeah. But Ben Franklin, of course, invented the bifocals, and real tricky thing in the 1700s to grind a piece of glass to just the right shape to work with your broken eye, when they didn't have all of the proper assessment tools either to see if your eye was working or what was wrong with it, etc. So, yeah, that was high-end technology at the time.
He's pretty smart.
He was a smart guy. So a lens, when we drew mirrors, for example, so let's go back to mirrors just for a moment. We drew mirrors. It didn't matter what kind of a mirror we drew. But what would happen is we found the focal point,
Mm-hmm.
and we drew our object, and we followed some rules. But the light would never go through. It would reflect into, but it would never go through the mirror. Right? And so mirrors are opaque. But lenses are transparent. And that's why we use the phenomenon of refraction to talk about the lens. I'm going to draw them differently too. I've still got my principal axis. You could draw the lens like this, but most people focus too much time on trying to draw the lens right. Okay, so what I recommend that you do is just to draw a straight line and then just say, hey, this is a lens. I know, not too artistic, but it works. Specifically, we're talking about double convex lenses. There are concave lenses as well, but we're going to focus on the double convex. That's the one I drew. It's the one that's thicker in the middle and thinner at the edges. You can physically feel it if you put the lens between your thumb and your fingertips, your middle finger or your pointer finger. And in a mirror, the mirror only had one focal point because the light itself stayed on one side of the mirror. How are the lenses different in that respect?
Well, lenses, there's two focal points.
And why do they have two?
Because the light goes through.
Right. So the light can focus on either side of the of the lens because there are two different focal points. So there's a whole host of things that we can do here. You want to draw the ray diagrams like we did with the mirrors. You go parallel just like you did with the mirror, and then you go through F. Oh, that's nice. The second time you go through F, and then you go parallel. And so since that was the tip of my arrow, this is the tip of the arrow, and it's upside down. We're going to talk about that because you don't see stuff upside down, do you?
Nope.
No. You're not aware that you see stuff upside down. How about that?
Now, isn't there a third wave that actually goes through the center of the lens?
Yeah, we could go with that rule too, but we just go straight through the center, and you'll see, even with my poor drawing skills, it's
kind of missed it there.
Kind of missed it, but it's pretty close.
Yeah.
So there are 3 rules that you can use, but what you see is they all intersect at the same point.
Okay.
You'll also note that there's no reflection taking place. This is refraction that takes place because this lens, so if this is air, and this is air, this lens is probably made of a piece of glass or plastic. Okay, so the bending happens when the medium changes, just like when we talked about refraction.
And then when it comes out the other end, it goes back to the way it was.
Correct. Because the light stays organized because the piece of glass or plastic is uniform in its shape. But notice that the light can go through both focal points. Okay, so that's the basics of it. It's not particularly complex. You can get into the details, and maybe your instructor will do that in class. There are equations, but here's the bottom line. If I redraw that picture, okay, this was always helpful for me. So here's my lens. Here's my object. Okay, I've got my focal length.
Now, are the focal lengths the same on both sides?
Yes, that's a good question. So the focal length, the location of f is the same on both the front and the back side of the lens. Now, this is where life gets tricky. We said in mirrors that all real images were inverted, right? So this back here, this was a real inverted larger image.
Right.
Okay. That's still true. But how did the real image show up on the other side of the lens?
Short and inverted as well.
Because it was inverted.
Right.
So what we didn't draw over there that we should be drawing is this is the human eye. Should probably label that. Right? And so you're collecting the light as it goes parallel, and then whether it be through the lens of your glasses or your contacts or the lens of your eyeball. Okay? And what happens here is that these lines are intersecting and forming on the back of your eyeball called the retina. Excuse me. And so what happens is on the back of your eyeball, sure enough, you see stuff upside down. That is weird. This actually happens, by the way. And you have another eye. Okay, and in between the two eyeballs, there is the optic nerve. And so both eyes are taking the same thing in. They both feed this information to the optic nerve, which is talking then to the brain. Your brain takes that information and knows to flip it over. Real images form on your retina upside down. So everything you're seeing right now, the ceiling is on the floor and the floor is on the ceiling. And an optometrist, when they look in the back of your eyes, they can see this. They see what you see, but upside down.
Isn't that crazy?
That is wild.
So it's like the world on its head?
No, the world is right side up. For some reason, for the rules of physics, I know the reason. The rules of physics tell us that things are going to form upside down, and then our brain knows to switch it back.
Amazing.
That is amazing. That is one of the most amazing things that I know about the human brain, and I'm sure there are many others. But
so then, with it forming upside down, this is kind of similar to an old-fashioned movie camera.
This is exactly like an old-fashioned movie camera, where you have to film the film in upside down or backwards. Slides and slide projectors have to drop those in upside down because it's the same concept.
And for those that don't know what a slide projector is, it's those little squares of old vacation photos usually.
Yeah.
Most probably don't know.
I have a slide projector in my room, actually.
Oh, yeah?
Yeah, it's buried away. But it is useful when we start talking about stuff like this, and we start talking about color and some of those other items. Now, unfortunately for us, the images can become complex. Like if you get inside the focal point, okay, you still got to follow your rules, right? It was parallel through F. And then it was through F parallel. And then it was through the center. Something like that. Seems like I've done something wrong. But what you get here is you get this intersection, and you get this image to form in front of the lens. And this is what happens with a magnifying glass. You've got the magnifier close to the object you're trying to see that's bigger, and if you look off to the side, you just see the image kind of floating in space, floating in the real space in front of the lens. Well, actually, since this guy is upright, this is a virtual, upright, larger image.
Is that why it's kind of hard to touch when you're looking at it?
Yeah, you can't. Right, you
It's
can't.
like,
And so a lens and a mirror, they have a lot of things in common. The rules are basically the same. They both have focal lengths, but the biggest difference, of course, is that the light can pass through the lens, and there are two focal points. Whereas a mirror, the mirror blocks the light, and there's only one focal point for the light to pass through.
and that kind of is the same thing like when you're just looking with your eyes, since your eyes are lenses. If you were to move your hand close enough to your face, you cannot see a crystal clear
Right.
part of your hand. It actually becomes fuzzy.
And so we have the same requirements for lenses that we do for mirrors. The object has to have light, so light has to be broadcast on it. And if you don't have that light, you can't see things in the dark with a mirror or with a lens because the object's not being illuminated. And we'll spend the next podcast talking about color and all of its wonderfulness, most of which I can't see. I think that covers lenses. There's some nice diagrams in your reading that we encourage you to take a look at. Take another look at what the focal point is, and maybe that'll help with some of the misconceptions we had about mirror focal points. So signing off, this is Mr. White.
Mr. Johnson.